Railway signalling is a system used to direct railway traffic and keep trains clear of each other at all times. Trains move on fixed rails, making them uniquely susceptible to collision. This susceptibility is exacerbated by the enormous weight and inertia of a train, which make it difficult to quickly stop when encountering an obstacle. In the UK, the Regulation of Railways Act 1889 introduced a series of requirements on matters such as the implementation of interlocked block signalling and other safety measures as a direct result of the Armagh rail disaster in that year. Most forms of train control involve movement authority being passed from those responsible for each section of a rail network to the train crew. The set of rules and the physical equipment used to accomplish this determine what is known as the method of working, method of operation or safe working. Not all these methods require the use of physical signals, and some systems are specific to single-track railways. The earliest rail cars were first hauled by horses or mules. A mounted flagman on a horse preceded some early trains. Hand and arm signals were used to direct the A-OE train drive versa Euro. Foggy and poor visibility conditions gave rise to flags and lanterns. Wayside signalling dates back as far as 1832, and used elevated flags or balls that could be seen from afar. Timetable operation, the simplest form of operation, at least in terms of equipment, is to run the system according to a timetable. A fixed schedule is drawn up with which every train crew must be familiar. Trains may only run on each section of track at their scheduled time, during which they have possession, and no other train is permitted to use the same section. When trains are running in opposite directions on a single-track railroad, meeting points are scheduled, at which each train must wait for the other at a passing place. Neither train is permitted to move before the other has arrived. In the US, the display of two green flags is an indication that another train is following the first, and the waiting train must wait for the next train to pass. In addition, the train carrying the flags gives 8 blasts on the whistle as it approaches. The waiting train must return 8 blasts before the flag-carrying train may proceed. The timetable system has several disadvantages. First, there is no positive confirmation that the track ahead is clear, only that it is scheduled to be clear. The system does not allow for engine failures and other such problems, but the timetable is set up so that there should be sufficient time between trains for the crew of a failed or delayed train to walk far enough to set warning flags, flares, and detonators or torpedoes to alert any other train crew. A second problem is the system's inflexibility. Trains cannot be added, delayed, or rescheduled without advance notice. A third problem is a corollary of the second: the system is inefficient. To provide flexibility, the timetable must give trains a broad allocation of time to allow for delays, so the line is not in the possession of each train for longer than is otherwise necessary. Nonetheless, this system permits operation on a vast scale, with no requirements for any kind of communication that travels faster than a train. Timetable operation was the normal mode of operation in North America in the early days of the railroad. Timetable and train order equals. With the advent of the telegraph in 1851, a more sophisticated system became possible because this provided a means whereby messages could be transmitted ahead of the trains. The telegraph allows the dissemination of any timetable changes, known as train orders. These allow the cancellation, rescheduling and addition of train services. North American practice meant that train crews generally received their orders at the next station at which they stopped, or were sometimes handed up to a locomotive on the run via a long staff. Train orders allowed dispatchers to set up meets at sidings, force a train to wait in a siding for a priority train to pass, and to maintain at least one block spacing between trains going the same direction. Timetable and train order operation was commonly used on American railroads until the 1960s, including some quite large operations such as the Wabash Railroad and the Nickel Plate Road. Train order traffic control was used in Canada until the late 1980s on the Armagh Central Railway and some spurs of the Canadian Pacific Railway. Timetable and train order was not used widely outside North America, and has been phased out in favor of radio dispatch on many light traffic lines and electronic signals on high traffic lines. More details of North American operating methods is given below. A similar method, known as telegraph and crossing order, was used on some busy single lines in the UK during the 19th century. However, a series of head-on collisions resulted from authority to proceed being wrongly given or misunderstood by the train crew, the worst of which was the collision between Norwich and Brundall, Norfolk, in 1874. As a result, the system was phased out in favour of token systems. This eliminated the danger of ambiguous or conflicting instructions being given because token systems rely on objects to give authority, rather than verbal or written instructions. Whereas it is very difficult to completely prevent conflicting orders being given, it is relatively simple to prevent conflicting tokens being handed out. Block signaling. Trains cannot collide with each other if they are not permitted to occupy the same section of track at the same time, so railway lines are divided into sections known as blocks. In normal circumstances, only one train is permitted in each block at a time. This principle forms the basis of most railway safety systems. History of block signaling on double-tracked railway lines, which enable trains to travel in one direction on each track, it was necessary to space trains far enough apart to ensure that they could not collide. In the very early days of railways, men were employed to stand at intervals along the line with a stopwatch and use hand signals to inform train drivers that a train had passed more or less than a certain number of minutes previously. This was called time interval working. If a train had passed very recently, the following train was expected to slow down to allow more space to develop. The watchman had no way of knowing whether a train had cleared the line ahead, so if a preceding train stopped for any reason, the crew of a following train would have no way of knowing unless it was clearly visible. As a result, accidents were common in the early days of railways. With the invention of the electrical telegraph, it became possible for staff at a station or signal box to send a message to confirm that a train had passed and that a specific block was clear. This was called the absolute block system. Fixed mechanical signals began to replace hand signals from the 1830s. These were originally worked locally, but it later became normal practice to operate all the signals on a particular block with levers grouped together in a signal box. When a train passed into a block, a signalman would protect that block by setting its signal to danger. When an all-clear message was received, the signalman would move the signal into the clear position. The absolute block system came into use gradually during the 1850s and 1860s and became mandatory in the United Kingdom after Parliament passed legislation in 1889 following a number of accidents, most notably the Armagh rail disaster. This required block signalling for all passenger railways, together with interlocking, both of which form the basis of modern signalling practice today. Similar legislation was passed by the United States around the same time. Not all blocks are controlled using fixed signals. On some single-track railways in the UK, particularly those with low usage, it is common to use token systems that rely on the train driver's physical possession of a unique token as authority to occupy the line, normally in addition to fixed signals. Entering and leaving a manually controlled block before allowing a train to enter a block, a signalman must be certain that it is not already occupied. When a train leaves a block, he must inform the signalman controlling entry to the block. Even if the signalman receives advice that the previous train has left a block, he is usually required to seek permission from the next signal box to admit the next train. When a train arrives at the end of a block section, before the signalman sends the message that the train has arrived, he must be able to see the end of train marker on the back of the last vehicle. This ensures that no part of the train has become detached and remains within the section. The end of train marker might be a colored disc by day or a colored oil or electric lamp. If a train has entered the next block before the signalman sees that the disc or lamp is missing, he will ask the next signal box to stop the train and investigate. Permissive and absolute blocks. Under a permissive block system, trains are permitted to pass signals indicating the line ahead is occupied, but only at such a speed that they can stop safely driving by sight. This allows improved efficiency in some situations and is mostly used in the USA, and in most countries is restricted to freight trains only, and may be restricted depending on the level of visibility. Permissive block working may also be used in an emergency, either when a driver is unable to contact a signalman after being held at a danger signal for a specific time, although this is only permitted when the signal does not protect any conflicting moves, and also when the signalman is unable to contact the next signal box to make sure the previous train has passed, for example if the telegraph wires are down. In these cases, trains must proceed at very low speed or less, so that they are able to stop short of any obstruction. In most cases this will not be allowed during times of poor visibility. Even when an absolute block system is implemented, multiple trains may enter a block with authorization. This may be necessary, for example, in order to split or join trains together, or to rescue failed trains. In giving authorization, the signalman also ensures the driver knows precisely what to expect ahead, and the driver must operate the train in a safe manner taking this information into account. Generally, the signal will remain at danger, and the driver will be given verbal authority, usually accompanied by a yellow flag, to pass a signal at danger, and the presence of the train in front will be explained. At locations where trains regularly enter occupied blocks, such as stations where coupling takes place, a subsidiary signal, sometimes known as a calling-on signal, will be provided for these movements, otherwise they are accomplished through train orders. Automatic block equals. Under automatic block signaling, signals indicate whether or not a train may enter a block based on automatic train detection indicating whether a block is clear. The signals may also be controlled by a signalman, so that they only provide a proceed indication if the signalman sets the signal accordingly and the block is clear. Fixed block equals. Most blocks are fixed, that is, they include the section of track between two fixed points. On timetable, train order, and token-based systems, blocks usually start and end at selected stations. On signaling-based systems, blocks start and end at signals. The lengths of blocks are designed to allow trains to operate as frequently as necessary. A lightly used line might have blocks many kilometers long, but a busy commuter line might have blocks a few hundred meters long. A train is not permitted to enter a block until a signal indicates that the train may proceed, a dispatcher or signalman instructs the driver accordingly, or the driver takes possession of the appropriate token. In most cases, a train cannot enter the block until not only the block itself is clear of trains, but there is also an empty section beyond the end of the block for at least the distance required to stop the train. In signaling-based systems with closely spaced signals, this overlap could be as far as the signal following the one at the end of the section, effectively enforcing a space between trains of two blocks. When calculating the size of the blocks, and therefore the spacing between the signals, the following have to be taken into account: line speed, train speed, gradient, the braking characteristics of trains, sighting, reaction time. Historically, some lines operated so that certain large or high-speed trains were signaled under different rules and only given the right-of-way if two blocks in front of the train were clear. Moving block equals. One disadvantage of having fixed blocks is that the faster trains are allowed to run, the longer the stopping distance, and therefore the longer the blocks need to be, thus decreasing the line's capacity. Under a moving block system, computers calculate a safe zone around each moving train that no other train is allowed to enter. The system depends on knowledge of the precise location and speed and direction of each train, which is determined by a combination of several sensors, active and passive markers along the track and trainborne tachometers and speedometers. With a moving block, line-side signals are unnecessary, and instructions are passed directly to the trains. This has the advantage of increasing track capacity by allowing trains to run closer together while maintaining the required safety margins. Moving block is in use on Vancouver's SkyTrain, London's Docklands Light Railway, New York City's BMT Canarsie Line, and London's Jubilee Line. It was supposed to be the enabling technology on the modernisation of Britain's West Coast Main Line, which would allow trains to run at a higher maximum speed, but the technology was deemed not mature enough, considering the variety of traffic, such as freight and local trains as well as expresses, to be accommodated on the line, and the plan was dropped. It forms part of the European Rail Traffic Management System's Level 3 specification for future installation in the European Train Control System, which will feature moving blocks that allow trains to follow each other at exact braking distances. Centralized traffic control. Train detection. Track circuits equals. One of the most common ways to determine whether a section of line is occupied is by use of a track circuit. The rails at either end of each section are electrically isolated from the next section, and an electrical current is fed to both running rails at one end. A relay at the other end is connected to both rails. When the section is unoccupied, the relay coil completes an electrical circuit, and is energized. However, when a train enters the section, it short-circuits the current in the rails, and the relay is de-energized. This method does not explicitly need to check that the entire train has left the section. If part of the train is left in the section, that part will continue to be detected by the track circuit. This type of circuit is used to detect the absence of trains, both for the purpose of setting the signal indication and for providing various interlocking functions, for example, not permitting points to be moved when a train is standing over them. Electrical circuits are also used to prove that points are in the appropriate position before a signal over them may be cleared. Modern UK trains, and staff working in track circuit block areas, carry track circuit clips so that, in the event of something fouling an adjacent running line, the track circuit can be short-circuited. This places signals on the track to danger and can be used to help prevent a collision before the signalman can be alerted. Axle counters equals. An alternative method of determining the occupied status of a block is using devices located at its beginning and end that count the number of axles entering and leaving the block section. If the number of axles leaving the block section is equal to those which entered it, the block is assumed to be clear. Although axle counters can provide similar functionality to track circuits, they also exhibit a few other characteristics. In a damp environment, an axle-counted section can be far longer than a track-circuited one. The low ballast resistance of very long track circuits reduces their sensitivity. Track circuits can automatically detect some types of track defect such as a broken rail. In the event of power restoration after a power failure, an axle-counted section is left in an undetermined state until a train has passed through the affected section. When a block section has been left in an undetermined state, it may be worked under pilot working. The first train to pass through the section would typically do so at a speed no greater than 20 miles per hour or walking pace in areas of high transition, reverse curvature, and may have someone who has a good local knowledge of the area acting as the pilotman. A track-circuited section will detect the presence of a train in section immediately. Fixed signals. On most railways, physical signals are erected at the line side to indicate to drivers whether the line ahead is occupied and to ensure that sufficient space exists between trains to allow them to stop. Mechanical signals equals. Older forms of signal displayed their different aspects by their physical position. The earliest types comprised a board that was either turned face-on and fully visible to the driver, or rotated so as to be practically invisible. While this type of signal is still in use in some countries, by far the most common form of mechanical signal worldwide is the Semaphore Signal. This comprises a pivoted arm or blade that can be inclined at different angles. A horizontal arm is the most restrictive indication. To enable trains to run at night, one or more lights are usually provided at each signal. Typically this comprises a permanently lit oil lamp with movable colored spectacles in front that alter the color of the light. The driver therefore had to learn one set of indications for daytime viewing and another for nighttime viewing. Whilst it is normal to associate the presentation of a green light with a safe condition, this was not historically the case. In the very early days of railway signalling, the first colored lights presented a white light for clear and a red light for danger. Green was originally used to indicate caution but fell out of use when the time interval system was discontinued. A green light subsequently replaced white for clear, to address concerns that a broken red lens could be taken by a driver as a false clear indication. It was not until scientists at Corning Glass Works perfected a shade of yellow without any tinges of green or red that yellow became the accepted color for caution. Mechanical signals are usually remotely operated by wire from a lever in a signal box, but electrical or hydraulic operation is normally used for signals that are located too distant for manual operation. Color light signals equals. On most modern railways, color light signals have largely replaced mechanical ones. Color light signals have the advantage of displaying the same aspects by night as by day, and require less maintenance than mechanical signals. Although signals vary widely between countries, and even between railways within a given country, a typical system of aspects would be: green, proceed at line speed. Expect to find next signal displaying green or yellow. Yellow, prepare to find next signal displaying red. Red, stop. On some railways, color light signals display the same set of aspects as shown by the lights on mechanical signals during darkness. Route signaling and speed signaling equals. Signaling of British origin generally conforms to the principle of route signaling. Most railway systems around the world, however, use what is known as speed signaling. Under route signaling, a driver is informed which route the train will take beyond each signal. This is achieved by a route indicator attached to the signal. The driver uses his route knowledge, reinforced by speed restriction signs fixed at the line side, to drive the train at the correct speed for the route to be taken. This method has the disadvantage that the driver may be unfamiliar with a route onto which he has been diverted due to some emergency condition. Several accidents have been caused by this alone. For this reason, in the UK, drivers are only allowed to drive on routes that they have been trained on and must regularly travel over the lesser-used diversionary routes to keep their route knowledge up to date. Under speed signaling, the signal aspect informs the driver at what speed he may proceed, but not necessarily the route the train will take. Speed signaling requires a far greater range of signal aspects than route signaling, but less dependence is placed on driver's route knowledge. Approach release equals, when the train is routed towards a diverging route that must be taken at a speed significantly less than the main line speed, the driver must be given adequate prior warning. Under route signaling, the aspects necessary to control speed do not exist, so a system known as approach release is employed. This involves holding the junction signal at a restrictive aspect in order that the signals on the approach show the correct sequence of caution aspects. The driver will brake in accordance with the caution aspect, without necessarily being aware that the diverging route has in fact been set. As the train approaches the junction signal, its aspect may clear to whatever aspect the current track occupancy ahead will permit. Where the turnout speed is the same, or nearly the same, as the main line speed, approach release is unnecessary. Under speed signaling, the signals approaching the divergence will display aspects appropriate to control the train's speed, so no approach release is required. Safety systems. The consequence of a train driver failing to respond to a signal's indication can be disastrous. As a result, various auxiliary safety systems have been devised. Any such system will necessitate the installation of trainborne equipment to some degree. Some systems only intervene in the event of a signal being passed at danger. Others include audible and/or visual indications inside the driver's cab to supplement the line-side signals. Automatic brake application occurs if the driver should fail to acknowledge a warning. Some systems act intermittently, but the most sophisticated systems provide continuous supervision. In-cab safety systems are of great benefit during fog, when poor visibility would otherwise require that restrictive measures be put in place. Cab signaling. Cab signaling is a system that communicates track status information to the train cab, where the train driver can see the information. The simplest systems display the trackside signal aspect, while more sophisticated systems also display allowable speed and dynamic information about the track ahead. In modern systems, a train protection system is usually overlaid on top of the cab signaling system to warn the driver of dangerous conditions, and to automatically apply the brakes and bring the train to a stop if the driver ignores the dangerous condition. Cab signaling systems range from simple coded track circuits, to transponders that communicate with the cab, and communication-based train control systems. Interlocking. In the early days of the railways, signalmen were responsible for ensuring any points were set correctly before allowing a train to proceed. mistakes were made which led to accidents, sometimes with fatalities. The concept of the interlocking of points, signals and other appliances was introduced to improve safety. This prevents a signalman from operating appliances in an unsafe sequence, such as setting a signal to clear while one or more sets of points in the route ahead of the signal are improperly set. Early interlocking systems used mechanical devices both to operate the signaling appliances and to ensure their safe operation. Beginning around the 1930s, electrical relay interlockings were used. Since the late 1980s, new interlocking systems have tended to be of the electronic variety. Operating rules, policies and procedures are used by railroads to enhance safety. Specific operating rules may differ from country to country and even from railroad to railroad within the same country. Argentinian operating rules in Argentina, operating rules are described in the Reglamento Interno tar Copyright Cnico de Operations, RITO. Australian operating rules In Australia, the application of operating rules is called safe working. The method of working for any particular region or location is referred to as the safe working system for that region. Operating rules differ from state to state, although attempts are being made to formulate a national standard. North American operating rules In North America and especially the U.S., operating rules are called method of operation. There are 5 main sets of operating rules in North America: Canadian Rail Operating Rules, used by most Canadian railroads; General Code of Operating Rules, used by many Class I railroads, Class II railroads, and many short-line railroads; Northeast Operating Rules Advisory Committee, used by many railroads in the Northeast U.S., Class I Norfolk Southern uses a unique set of operating rules. Class I CSX Transportation uses a unique set of operating rules. UK Operating Rules For the UK, the operating rule book is called GERT 8000 Rule Book, or more commonly known as the Rule Book by railway employees. It is controlled by the Rail Safety and Standards Board, which is independent from Network Rail or any other train freight operating company. Most heritage railways operate to a simplified variant of a British Railways Rule Book. Italian Operating Rules In Italy, railway signalling is described in a particular instruction called Regolamento Segnali. Indian Operating Rules In Indian Railways operating rules are called the General Rules. The General Rules are common for all zonal railways of Indian Railway and can be amended only by the Railway Board. Subsidiary rules are added to the General Rules by zonal railways, which does not infringe the General Rule. Corrections are brought about from time to time through correction slips. See also. References. Bryan, Frank W. Railroads Traffic Control Systems. Trains. Carnegie Publishing Company. Archived from the original on October 22, 2013. Retrieved August 16, 2006. Colburn, Robert. A History of Railroad Signals. The Institute. Institute of Electrical and Electronics Engineers. Tech Focus. Archived from the original on October 22, 2013. Retrieved October 22, 2013. General Code of Operating Rules. BNSF Railway Company 2005. External links. The Signal page is a website about railway signaling, worldwide, railserv.com. Signals and Communications, Railways, History, Signaling, Engineering, 1, 2, 3, 4, and 5. Signaling Record Society, the Institution of Railway Signal Engineers, World Railway Signaling Database.